In this lesson, I'm going to introduce you to the third and last value theorem in AP Calculus. To remind you, we've already learned about the extreme value theorem, the intermediate value theorem, and the last theorem is called the mean value theorem. So our learning target is to apply the mean value theorem to differentiable functions. So since we have three theorems that are all value theorems and they are similar but yet have differences, we're going to use this chart to organize what we know about the theorem, its requirements, and what it's used for. So just a comment on how to set up your chart so that you can set it up the same way every time and hopefully help you remember the three theorems. I like to put the EIM, the name of the theorems, in the top row, and that's alphabetical order. The second row is the requirement of the function to use each theorem. So you may remember that the EVT and IVT both require that the function be continuous. The mean value theorem requires that the function be differentiable, so it has an extra requirement upon that function. We do know that differentiability implies continuity, so we don't need to add that to our chart every time, but just know that that thought is there. We're going to use the last row of our chart to remind us what the theorem means as far as the function is concerned. For EVT, I like to put M&M to remind me that it's required, or it guarantees a maximum and a minimum for that function. For IVT, that's all about f or y values. So the function takes on every y value between two given y values. And our new theorem, MVT, actually talks about f prime, or the derivative. And if you looked ahead to this formula, you do see that we have f prime defined as the average rate of change. So in mentioning that formula, it is the only of the three theorems that does have a formula attached to it. So you want to think about f prime being equal to the average rate of change, which is why it's called the mean value theorem, because mean is another word for average, I'm sure you remember. Let's look a little more closely at our formula that we'll be using for MVT. If you have two different colors to highlight the two sides, that would be great. We're looking at the derivative is equal to the average rate of change, and we know that the derivative is the instantaneous rate of change. An example I like to use to put this in context of real life that everyone understands is that when you take a trip in a car, you have an average speed and you have an instantaneous speed. So let's say on your road trip, your average speed was 50 miles per hour. That means sometimes you're going less than 50 miles per hour and sometimes you're going over 50 miles per hour. But at some point during that trip, your instantaneous speed will equal your average speed, because to get from a lower speed to a higher speed, you are going to have to pass through that instantaneous rate of speed, which is equal to your average. So it's also a nice connection to IVT since we're talking about y values. Let's go ahead and define these terms of the formula in words as well. So we already talked about what goes in this first line here. The instantaneous rate of change equals the average rate of change at some point C. The second line, let's fill in and talk about the slopes of the tangent and secant lines. So we know that the instantaneous rate of change, or the derivative, is the slope of the tangent line. It's going to equal the slope of the secant line, which is represented by the average rate of change. I think it's really nice to look at this thought visually down here on this graph. So if you'll label it with me, we have some points at A and B, so A f of A, B f of B. We draw a line through those 2 points, and that gives us the secant line, or the average rate of change. At some point C, between A and B, there's going to be a tangent line that is exactly parallel to the secant line because their slopes are equal. And what the mean value theorem does is help us find where that C value is that makes these two lines exactly parallel, or equal slope. So our last line here just summarizes what we saw in our graph. The tangent line is parallel to the secant line because they have the same slope. Right below our graph, we see we have something called Rolle's theorem, which is called a corollary to the MVT. And corollary just is a fancy word for saying it's an addition or it's a special case of the MVT. And the special case is when the function value at A and B are equal. If that's true, then there's at least one value c such that the derivative, or the instant rate of change, is equal to 0. I think this corollary makes a lot more sense when you look at it from a graphical perspective. So if we have a function whose function value at a and b are equal, meaning they have the same y value, when you draw that secant line through the 2 points, the slope of the secant line is going to be 0. And so when we find the value of c, where the tangent point will be, and the tangent line goes through that 1 point, its slope is going to be 0 as well. I think algebraically this makes a lot of sense if you look at the formula. If f of b and f of a are equal, when you subtract two equal amounts, you of course are going to get 0 divided by any number, which is 0. And for the last thought on this Rolle's theorem, since we have a secant line that goes through two y values that are equal and have a 0 slope, it creates a perfectly horizontal tangent at the point C. You'll find that we're going to apply this theorem most often when we're given a table of values and ask if the derivative could ever equal 0. All we'll have to do is look for two function values that are equal, and we'll be able to conclude that yes, it equals 0 by NPT, or fancy if we remember to say Rolle's theorem too. Let's go ahead and take a look at our first example, and I really like this problem because it breaks down the NPT process into bite-sized steps or baby steps. So we are given some information. Basically, they're describing what they have here. They've graphed the secant and tangent lines that are parallel according to the NVT. And we're going to go ahead and try to apply the formula just one piece at a time. So part A asks us for the average rate of change over 2 to 5, which are where the points of the secant line occur. We've had a lot of practice with average rate of change this year, so this should be a good review. So f of b minus f of a over b minus a. They've given us a is 2, b is 5. So we put that in our formula. And then from the graph, the function value of 5 happens to be a y value of 5. And the function value of 2 is 2. So when we subtract and reduce, we get 1. Positive 1 is the slope of our secant, so our secant slope. And you can confirm that by doing rise over run, which is 3 over 3. Part B reminds us that we always need to make sure that our function meets the requirements or satisfies the hypothesis of a theorem before we use it. So the requirement of the mean value theorem is that the function be differentiable. You'll see that we have a nice polynomial, which is a parabola, and so we can state, yes, f of x is differentiable, and then I think it's really safe to always conclude and therefore continuous on 2 to 5. Part C says application of NVT. So basically, once we decide that we're allowed to apply NVT, let's go ahead and see what it says. And basically, they're just asking us to restate the formula here. F prime of C will equal f of b minus f of a over b minus a. And luckily for us, we've already gone through that process in part A and found that value to be 1. So we can conclude that the derivative of f somewhere will equal 1. So in part D, we're finally going to get to apply the NVT formula now that we've taken the baby steps to set it up. So we need to find the derivative of f evaluated at c. So we first need to look at our function f and find its derivative. Luckily, it's going to be an easy power rule with a chain rule of just 1 and then a constant. So let's go ahead and calculate that. So I brought my power of 2 down to my coefficient. That gave me 2 times x minus 3. That's now to a new power of 1, or first power. And then the derivative of that constant plus 1 goes away to 0. So I'm left with 2 times x minus 3, and I distributed that to 2x minus 6. So f prime of c simply means we're taking the variable c and replacing the x in our derivative with c. So this becomes 2c. Okay, that's better. 2c minus 1. Again, we're replacing c for the x in our derivative, and that becomes something really easy to solve. We get 2c equals 2. C equals 1. Sorry guys, you're probably yelling at your computer screen. This was a 2c minus 6. I miscopied that. So then it gives us 2c equals 7. C equals 7 halves. So let's talk about what our answer means. We found that c is equal to 7 halves, which is also 3.5. And this is the c or x value where the tangent point must occur. So if we look back at our graph at 3.5, put our tangent point, that is exactly where our tangent line will be perfectly parallel to our secant line.